So my name is Yanez. I am actually an undergrad here, and Brian is my advisor. So that's why our talks are related. He basically passed this project on to me because he had some more interesting things to do with CHARON. So I inherited PLUTO. What's kind of interesting, just as some background, is that, as we just discussed, ultimately the answer for what I'm about to ask is that CHARON's really tiny, can't really hold on to all these same volatile ices. They can kind of just get blown away because it doesn't really have an atmosphere, which is where we tend to find these. But ultimately, PLUTO and CHARON are really close together. So when you compare this to our own Earth and Moon, it's about a factor of 80 difference. So CHARON's about 80 times closer to PLUTO than our Moon is to our Earth. In addition, they're tidally locked and triple synchronous. What that means is that PLUTO and CHARON are always showing the exact same side to each other. So as PLUTO orbits or rotates, CHARON orbits at the same time frame and the same rate. So they're always facing each other at the exact same side, which is pretty interesting. They're really close together, always facing the same side to each other, but they're different. And they were formed in the same giant impact, which means that at this, basically, as Brian explained, they had a grazing impact, all this stuff gets thrown into the air, so they all had the same beginning material, but they evolved really differently, ultimately answered by the fact that CHARON's really tiny. But what you do see on Pluto's surface is basically 3 volatile ices, N2, carbon monoxide, and methane. And these are kind of important because that's basically all we see aside from water ice. And as Brian mentioned, we really only discovered the water ice because of New Horizons. So based off of ground-based research, the only things we're seeing are these 3 volatile ices. Those are the only things we can really track and keep ideas of how much and things like that. CHARON has none of them, so it's kind of interesting. Why are they formed so differently? Once again, CHARON's really tiny. So what we did was we obtained data from the Apache Point Observatory in New Mexico across 9 nights throughout 2 years. And in a second, I'll explain why this is really important, why we did it in a specific way. But ultimately, what we did was use a 3.5-meter telescope. We shined it up at Pluto. We took all this data. And because we're looking through the Earth's atmosphere, we have a bunch of correction to do and reduction to do. So basically, we get really nice images. And then we have to take those images and turn them into squiggly, curvy lines that actually show us something, which takes a while and is really nice. But as you'll see, it can sometimes make them kind of ugly. So matched pairs. What we did was we had a matched pair system. So what makes this important and why this Pluto surface composition results are more important is that we were able to erase some of the incidences that can make our data misleading. And what we were able to do was, so this is you on Earth, all smiley and happy, right? Now what we call the sub-observer latitude is that Pluto is beneath you. So the enemy's gate is down, okay? And what this means is that for each of our matched pairs, we were on the exact same hemisphere of Pluto, at the exact same latitude and longitude, which means that we were staring at the exact same point every time we made results. And it's a 420-day cycle, which means that June of 2013 matches with August of 2014, June of 2014 matches with August of 2015, et cetera. And what this does is that if Pluto was slightly more rotated or slightly tilted differently because we weren't doing this in this 420-day cycle, we would be able to say that, oh, maybe these changes we're seeing in surface composition aren't actually due to the fact that we're seeing changes or in abundance. It's that we're looking at maybe the polar caps instead of the equator or something like that. It's that, basically the latitude can change a little bit, but you're still looking at the same area, the same hemisphere, same point, so that we're able to erase viewing geometry errors and rotational phase errors. So over the course of 2001 to 2013, William Grundy made a series of observations of Pluto. And he averaged them out over the 12-year time span, which is what this is. And we ultimately used his last year of data in June in 2013 to compare with our own. So this is really important. This is great. We got an average spectra of Pluto, which means that we looked at Pluto, we got this stuff, we see what's absorbing on its surface, and we can see what it's made out of. That's great. But by using our matched pairs, we can study how it's changing over time on a short time scale and see if that's actually happening and if we're seeing these changes in abundances based off of how deep these curves get. So that's why this is really important. That's ultimately what we're looking for is, can we see changes on Pluto's surface in the time scale of Earth years? Because when you look at Pluto's orbit, it's 248 years long, which means that in the course it's existed, which is only about 80 years, that's about how long we've known Pluto's discovered. We haven't even seen half of its orbit. And we've only had spectral data for the past 40 years, from the 1970s, which means that we've only seen what it could possibly be made out of in 40 years. And during that time, it was at perihelion, which means it was the closest it can be to the sun. So we've only seen it approaching the closest and moving away from the closest. The information we're getting from New Horizons and ground observing now is actually the farthest we've ever seen Pluto from the sun and been able to get results. So it's kind of an important time right now, because we're seeing Pluto in a place we've never seen before, and we're seeing how it can be changing. So pay attention to this. There's a specific little bloop and then 2 humps, okay? This is a methane band. And it's kind of important for specifically what we were looking for, which was changes in methane due to the fact that it would be moving away, getting colder, and methane is less volatile, which makes it more inclined to precipitate down. So we were ultimately trying to see, is there a change in methane? So this is our data. As I mentioned, it can get really ugly. That's because, as I mentioned, we're looking through Earth's atmosphere. Earth's atmosphere has a bunch of water vapor that likes to gunk up our data. Our corrections weren't going so well this week. So because of that, we have a lot of ugliness. But you can still see the little blip and a double hump structure, which is still methane. So we're still able to use this because when we're comparing this to the past ones, they also have these caloric absorption areas. So they will cancel out eventually and work out to give us an answer that's kind of correct and can get better, which is what we're aiming for. But looking at that same methane hump and subtracting these 2 areas after normalizing the y-axis, which is albedo, we're able to get this. This doesn't look very pretty either. But if you notice right here, at just about the same wavelength as right here, there's a dip. And what this dip means is so that this was taken from subtracting data from 2014 from data from 2015, or vice versa. Data from 2015 from data from 2014. So we're able to say it's because this is a negative dip, we know that there was more methane in 2015 than there was in 2014. And although this is still preliminary, see, it could potentially be an increase. We're hoping that it actually is. And what this means is that we are seeing an increase in methane in a period of just 1 year. And I mean, we're looking at ultimately a course of 3 to 4 years, but in 1 year, potentially there's already a difference, which is really important, as I mentioned, because we are moving away, Pluto's moving away from the sun, that we're seeing it get colder, we're seeing it precipitate down, and we might actually be able to see how its surface is evolving over the course of just its orbit, which is pretty cool. So how does this relate to astrobiology? So what you guys know as chin-ups, I know a sponge, which is a Mexican pastry that basically has jelly marshmallows on top of a cookie. And I just like it much better than chin-ups because sponge is so much more fun to say. So out of the 6 elements that we know are required for macromolecules and for life eventually, Pluto has 4 of them. It has methane, carbon monoxide, and nitrogen. So it's already 2/3 of the way there. And we know that it's not doing too much, but we know cryovolcanism might be an idea. We know that there's water ice. We know that stuff's going on. And with this increase of methane on the surface, we might be seeing some really interesting things going on. So it's kind of important that it already has these 4 and what these 4 could mean for the beginning stages of macromolecules like carbohydrates or non-methane hydrocarbons like ethylene, ethane, and acetylene. So it's pretty cool. So UV radiation is also something really interesting. Pluto gets about 1/900th the UV radiation that we receive, and that's just to its atmosphere. That's not counting what gets through its surface. Well, methane does most of the absorbing in its atmosphere. Well, if methane is the one that's precipitating down, what's going to happen to its atmosphere? Now the UV radiation isn't being blocked there. The UV radiation is actually hitting its surface. So if we revisit Pluto's surface, there's a lot of funky things going on with Sputnik Planum. We don't know what's going on there. We just found out a bunch of interesting information. No one knows what's going on. But over here, which you can't really read, it says Cthulhu Regio. And Cthulhu Regio is basically organic goop. So the best analogy I can come up with is if you have a big old pile of snow in a driveway or a parking lot and it melts away, what you're left with is like black, gunky, solid goop, right? That's basically what that is, except it's methane instead of water ice. And it's toxic, it'd probably kill us, but it's goop, and it's solid goop coming from methane. So if more of this methane is precipitating down in the course of its 248-year orbit, we could be seeing more of Pluto turning to goop, which would be interesting because we know that if it's going to be like this, it means that there's more absorption happening at the surface instead of the atmosphere, which could potentially change other types of composition and cause interesting reactions and interesting things to happen on Pluto's surface that we haven't been able to observe before. And this is kind of important because when you look at it in a big picture scale, Kuiper Belt objects far outnumber other types of planets like Mars or Earth-like planets. And because of that, if we aren't studying them and seeing these changes and seeing these evolutions just because they're on a really long time scale, we won't know what the full potential is of our entire universe. The fact of the matter is that looking at Pluto, we know it's going to change, and we've never seen it change this way before. And it's a great way to look at it because we know that methane is precipitating. We can study that. We can see how it's changing over this next 20 to 100 years as it moves farther and farther away. And we've still never seen it when it's at the farthest point it gets from the sun. So in looking at all of these, it's really interesting because we just don't know what's going to happen. And using it as an example to look at other planets and other galaxies or solar systems is really important just for understanding how our planets actually evolve. Just on a basic planetary evolution scale, we can look at our Earth, we can look at Mars, we can guess and make theories and figure out what's going on. But Pluto, we can actually see what's going on. We're seeing it change over just the course of 200 years, which is really cool. And this is just really interesting. So this is how our images have evolved since the 1990s. So this is like our first ever image of Pluto, and this is what we got last year. So just to put it in perspective, you know, in 20 years, we're seeing a huge amount of information gained. And we're only going to see more because it's moving away, because it's getting farther away, and because we're able to already track this precipitation. It's really cool and really interesting. And this short-term scales give us a better idea of how things are going to evolve and give us an idea of what to look for in the future. And that's it.
Questions?
Hello? Oh. This might be a very ignorant question because I'm not a remote sensing person. How do you filter out methane in our atmosphere versus methane on Pluto?
So there's not, when we're looking through, the main thing that we actually get blocked from our atmosphere is water vapor. Everything else is kind of negligible because we're looking past it and it doesn't absorb as much for what we're seeing, so we don't have to really care about it. Like what we're seeing, like Pluto's atmosphere, for instance, doesn't affect our data. We're just looking at Pluto's surface composition. But the water vapor in our absorption really affects how our data is changing. But our methane doesn't really, as far as I know, unless I'm totally wrong.
Okay, so this might be kind of out there, but you know, on Titan we have these possible lakes of hydrocarbons. Would you expect to see anything in liquid phase on the surface of Pluto?
Probably not. It's way too cold. But we are seeing, same in that Cthulhu regio, we're seeing tholins. So we're seeing a lot of non-methane hydrocarbons, which brings us to say that we'd probably see them in that goopy, maybe snowish kind of form or an ice form. But we really wouldn't see it in a liquid form like a lake. It's just way too cold.
Other questions? I guess I had a question. So when you were talking about how you were going to get more organic goop deposited on the surface, would you expect that that organic material was already made, or do you think you're going to be making the material from sort of surface processes once the methane is snowed out or whatever?
So the goop is coming from the UV radiation reacting with methane. So the goop is just basically non-methane hydrocarbons. So it's kind of being made in the atmosphere and kind of being made once it hits the surface. It's just the reaction of methane with UV radiation. So it just depends on where it's hitting. But once it precipitates down, that's just methane falling to the surface because it's too cold. So it's kind of already there. It's more what's it going to do once it gets there. That's what we're more interested about, because then it's retaining more UV radiation and other types of radiation. It's absorbing all of that. So I don't know what it's going to do, but it's kind of being made just by the interactions of UV radiation and methane.
Anybody else have questions?